So today we are going to kind of follow up from our discussion of how to represent strain or stress, as a tensor property, and now we're going to start to talk about strain. So today, strain is also going to be represented as a second-rank tensor. Let me change this to black to begin with. We're going to talk about strain today, and we're going to represent strain as this epsilon value. So, but first, let's kind of start just like we did kind of previously. So when we are doing our uniaxial tensile test, so we know now that if we're pulling in this direction, we're going to apply some stress sigma 2 in this coordinate system. So our stress tensor is just 0, 0, 0, 0, sigma 2, 0, 0, 0, 0. Now, we want to figure out, once we pull on this material, we know that if this is time t equals 0, where we just start to stress that material, after you pull for some time, that material is going to elongate. So if this is our initial distance, our initial kind of dimensions, it is going to increase here. And also it's going to thin. We'll talk about that a little bit later. So we are going to change from this initial length, so we're going to kind of label this as L naught, to kind of this final length L. So in this type of scenario where you're mechanically pulling on material and you need an axial tensile test, the strain, the engineering strain, just like last time, is just going to be L minus L naught divided by L naught, or equivalently delta L over L naught. So the change in length over your original length. And you'll notice here, again, this strain is unitless. And this is engineering. That subscript E is engineering strain. So that is what we're going to be dealing with, again, typically just like engineering stress. Now, you can also have true strain. So true strain would be essentially, just like we had the instantaneous area, it would be the basically this partial derivative dl over L naught again. So you could basically calculate the true strain by basically taking this integral from L1 to L2, and you do dl L, and you'd find that this is approximately natural log of L2 over L1. But anyways, we're not going to deal too much with true strain in this course, but again, if you take another mechanics course, true strain does exist. But we are going to focus on this guy right here. So that is your strain definition for essentially a normal stress. So we talked last time, the diagonal components of your stress tensor here, these are normal stresses, and associated with them are normal strains, this epsilon right here. Now, if you're dealing, I'm going to kind of erase now, if you're dealing with shear stresses, so we know that we use sigma typically for normal stresses. There's only one L. We use tau for shear. And we know now that there's an associated, for normal stresses, there's also normal strains. For normal shear, or for a shear, there's a shear stress, and this is going to be essentially our shear strain value here. So let's look at an example right now for how do we calculate shear strain? Well, let's imagine we have, this is again our starting at time t equals 0. I have my little block element like this, my square. Now, at time t equals t1, I am going to apply a shear. So I'm going to shear this material this way. Well, the material afterwards is going to look like this, shifted from its original position, like this here. So it's shifted. Now, what happens? It's shifted some amount. We're going to call this amount here basically dl. So dl right here. 1 second. Some change in distance, and there's some angle associated with this as well. So your shear strain is going to be basically the same definition, dl over your initial length L, and that is going to be I know at Pacific, you know that you've taken statics. I know you're all sine and cosine experts, so dl over L is just going to be tan theta. So that is how you would calculate your shear strain, and this is kind of the shear. This notation here for strain is kind of like your engineering shear strain. So we're going to see there's a difference between this notation of like 1, 2 versus the tensorial notation. We're going to actually see that in just quite a bit. If you just have a situation where you had pure shear, just like in our uniaxial tensile testing method, we saw this relationship between Hooke's law, so Young's modulus times your normal strain. You also have a similar scenario with shear, where G is your shear modulus. More a little bit on that a little bit later. So shear modulus, and this is going to be your engineering shear strain. Yeah. So how do we define, or how do we kind of represent our basically shear, or excuse me, strain as a second-rank tensor? Well, we're going to use essentially the same definition. So second-rank tensor, we're going to have, again, you could have strain in the same kind of directions that we kind of talked about last time. So you could have epsilon 1, epsilon 1, 2, epsilon 1, 3, epsilon 1, 2, excuse me, epsilon 2, 1, excuse me, epsilon 2, 1, epsilon 2, 2, epsilon 2, 3, epsilon 3, 1, epsilon 3, 2, epsilon 3, 3. So this is your second order strain tensor. Now, same idea if we're in equilibrium, our representative volume element, and we don't have any rotation going on, we are going to say that these two are equal to each other, that this guy and this guy are equal to each other, and these two are equal to each other. So we go again from 9 independent to 6 independent. Make your life a little bit easier. And again, this follows from, you'll see, we're going to probably talk about this in just a little bit, but you can relate stress and strain. So we can relate sigma ij through sigma ij kl to epsilon kl. This is assuming that we are not linear elastic and isotropic. So this is a second rank, these two, second. So they have, remember, 9 components. This is a fourth rank tensor. This has 81 initial components. That math becomes extremely, extremely hard. You really need linear algebra to solve this one, but we're getting a little bit ahead of ourselves. So forget about that for just a little bit. Let's rewrite our strain tensor, and let's see what it looks like. So just like last time, epsilon 1, 2, epsilon 3, epsilon 1, 2, epsilon 2, 2, epsilon 3, epsilon 1, 3, epsilon 2, 3, epsilon 3, 3. 6 independent components right here. And that is your strain tensor. Now, unfortunately, here's where we kind of run into a hiccup. So when we were talking about stress, our stress tensor here, let's kind of write it out as well. So 1, you can never get too much practice writing these out. Sigma 3, sigma 1, 2, sigma 2, 2, sigma 2, 3, and sigma 1, 3, sigma 2, 3, sigma 3, 3. Fortunately here, our definition for, so if I write sigma 1, 2 is equal to tau 1, 2. Unfortunately here, epsilon 1, 2, so our tensorial definition of strain does not equal our engineering definition of shear strain. Why is this the case? Well, this is where we're going to have to invoke something called infinitesimal strain theory. This is going to get a little complicated. I don't want you to worry too much about kind of following too close. I mean, it's great to kind of know this definition, but it's not crucial. But it's just more for your information. If you're interested in kind of a longer video or a longer explanation of this derivation, I'd be happy to kind of provide it for you. But basically, the nuts and bolts of it is we are going to define our tensorial definition of strain is going to be defined by this derivation or this equation. So the partial of displacement, of u with respect to I dxj plus duj. We're going to explain all this in just a second. So this is supposed to be a j. This is supposed to be a j. And this we're gonna kind of scroll back into our notes so you can see the LaTeX. So excuse my handwriting for just a second. So mu or u, excuse me, u is your displacement vector. Vector. And we are going to actually also define a deformation tensor. Deformation tensor is just going to be this Eij, where your deformation is going to be described by the change in your displacement, I, over the change in, again, the initial length, basically your x coordinate, j. So let's kind of draw in, and luckily, we just said that epsilon 1, 2, So our tensorial definition of strain does not equal our engineering shear strain, but luckily epsilon 1, 1 is equal to our definition of epsilon 1, 1. So we're going to kind of prove that in just a second. So let's take a look and start to draw out an example of how this can work. So I am going to draw basically my initial box. So I'm going to make this blue. So this is my initial box here. I'm going to pull my box, and actually let me label a little bit better, x2, x1. I am going to change the length of this box, and I'm going to pull it upward, or I'm going to actually compress it. So I am going to compress this here. Don't worry about the sign. Actually, let's have my red be my initial. This red is my initial size of my box. Then I pull it up. So there is this change. I'm going to switch to green. So this change here is du. So I displace some amount, u2, u in the 2 direction. That's my displacement over my initial length, x2. That is equal to E22, which is equal to epsilon 2. That tells us that if I want to figure out what is my epsilon 22, it is just going to be, epsilon 22 is equal to E22. You could kind of see this from this definition in here. So you could kind of prove this. Again, if you flip this, it doesn't matter. You still get that same value. We're equal here. The problem comes into play when we're dealing with our tensorial definition of shear strain. So let me erase really quick. I'm going to erase this here. Now imagine, I have to erase this unfortunately. Switch my colors and go back. Yeah. Now imagine instead that we have our initial box is red, and now I change and I shear from both sides. So this is not going to look pretty, but please bear with me. So this down, sheared, sorry, I'm going to do a little bit shallower. Again, not drawn to scale, but just exaggerated so you can kind of see these dimensions. So I'm going to have in here, there's going to be some displacement, some deformation E12, and some deformation E21. Now, from this definition, from the definition of my, basically what is my definition of tensorial strain, which we have right up here, let's think about what is my definition of my engineering shear strain. Well, engineering shear strain is just the displacement partial u, change displacement of 1 divided by the initial x2 length. If I want gamma 2, it is partial u2 partial x1. What is my definition of epsilon 1, 2? Let's look at it right here. Epsilon 1, 2 equals 1/2 times d mu 1 divided by d x2 plus d mu 2 dx1. So if I plug that in here, this is also equal to, epsilon 2, 1. Plugging in those values here, if I want to figure out, what is my definition of that strain, you'll see, you can do the math out, we're off by this factor of 2. Epsilon 1, 2 equals epsilon 2, 1, which equals half of our engineering shear strain here. That is the issue. So our tensorial definition is off by this factor of 2. Now, what does that do here? All it means, again, practically speaking, let's go back to the notes. All it's saying here, this is just, again, just derived, previously, as we just kind of did. We're off by this factor of 2. So if this is our tensorial definition of strain, this is how we represent it if we are plugging in, again, because typically we measure shear strain experimentally using our experimental shear strain. You have to be careful. Are you given the tensorial strain tensor, or are you given values? Are you measuring strain in terms of the engineering shear strain? So you just have to be careful, account for this factor of 2, and then you're good to go. So one last thing before we leave for today, Poisson's ratio. Now, when we pull this material, it not only, so let's look at our uniaxial tensile test. So if I pull my material, 2, 1, when I pull it, it extends, right? So it increases in size, in length here, in the length of the 2 direction. So when I apply sigma 2, 2, it gets longer. But you'll notice how I'm drawing it here. This is the change after you pull. It also contracts in this lateral direction. Again, you could see that if you kind of play around with silly putty. So this contraction, or the ratio of the kind of axial strain, so the axial strain would be this kind of increase in length here. The ratio of that axial strain to the lateral compression is described by, same thing is said here, is described by your Poisson's ratio, nu. Poisson's ratio is a very, very, very important kind of parameter. And again, we have some kind of known values that you kind of want to have in the back of your head. So let's kind of move on to the next page. You can also, the Poisson's ratio, there's some kind of critical values here. So if you're working with, again, ceramics, if you're working with metals, and you're working with polymers, and remember, nu is equal to your minus E lateral, so your contraction. So if we're contracting, we know that the lateral contraction, this epsilon, this is going to be negative. We know that our axial is in tension, so this is positive. So Poisson's ratio is, generally speaking, always going to be a positive value. Now, there are some negative materials with a negative Poisson's ratio. Those are really unique materials that you kind of have to design. I can't think of off the top of my head of a material with a negative Poisson's ratio kind of that you find naturally, but again, they can exist. But the values that I want you to kind of start to memorize, just like what we saw, and actually we'll do a little quiz here for Young's modules as well. For ceramics, my Poisson's ratio is generally around 0.2. For metals, 0.3. For polymers or biomaterials, generally about 0.4. 0.4, 0.5. I'd say 0.4 is a good value. Now, obviously those values can kind of change, but those are just some general good values to know. Now, why would this be the case for ceramics, metals, and polymers? Why does it have the largest Poisson's ratio? Well, if I have a large Poisson's ratio, it means that I have a large lateral contraction, meaning it's easier for it to kind of decrease in the lateral direction. So what's going to happen here? I mean, why is that the case? Well, we know that polymers are kind of more compliant, right? Less stiff. They're more ductile. So as we pull, it's easier to contract in that direction. We know the ceramics have a Young's modulus of about 300 GPa. Very stiff, hard to pull and stretch those bonds. So it's not going to basically contract as much. Metals, again, as you'd say, around hundreds of GPa. And polymers, of course, they're difficult, 10 MPa to about a gigapascal. But polymers, again, my favorite material, they're difficult, therefore fun to study because they do lots of weird stuff. So that's about it for today in terms of the kind of the tensorial definition of strain. So don't worry too much about infinitesimal strain theory. Just know about that kind of factor of 2 difference. And yeah, that's all I've got for today. Let me know if you have any questions or if you want to kind of do some more problems on this. We're going to get to a lot of problems in a bit. So today's lecture is kind of more theory. We're going to get into kind of how to actually solve biaxial stress problems in a bit. So yeah, exciting things are to come. So I hope you've enjoyed this, and yeah, have a good one. Bye.